The packet types in OSPF. This number, like 1, hello, 2, database description, 3, link state request, 4, link state update, 5, link state acknowledgement. These numbers are also seen when you capture a packet. When you see 3, it always means link state request. This number is mapped to this packet. So this is not a serial number. This is a number that is given to this type of packet. LSU is always packet number 4. If you are using Wireshark or when you are using debug, a debug command, you will see this number. For example, if you see, I think that should be, here it is. If you see here, it is showing 1. T type. T stands for type. So tell me, what packet is this? It's a hello packet. Yeah. Yeah. So it is good to know in the order, or it's good to know the number for the packet type. LSU is always packet type 4. Okay, so database description is what? Database description is the summary of LSDB. That is database description. You know about link set request. Summary means LSDB is detailed of what? Topology. Detailed topology information is saved in a database called LSDB. We learned that in the previous class. Every router will have LSDB, but when they share to the neighbor, they don't share LSDB. They share the summary of LSDB. If it shares detailed LSDB, the consumption of CPU and bandwidth will be very high in a big network. So it is always the summary of TB LSDB is shared, which is called as DBT. Have you seen aeroplane? You have seen aeroplane tickets. You see the boarding pass. This one is the summary about most appropriately. This one is the summary of the guy who is traveling. Or if you see, this is also looking like a summary. He belongs to first class. And this EK stands for something. It has got some meaning. And this 10B is the seat number. So it's a summary of the traveler. It's not detailed, but when you see that, you will get the complete summary, some complete information about the person. A summary. That is what DBT. So DBT, database description, you should not think that something is missing. No, there's nothing missing in it. It's a detailed. but it don't look detailed, but it looks summarized. It is as equal as detailed. That's what I want to say. It's small in size, but at the same time, it has got more the complete information what you see in LSDB. Next is the LSR, link state request. Link state request is made during the adjacency state. For example, a router is sending an LSDB. I said it is a complete LSDB sent in the form of summarized DBD. But the receiver, if he is not fully understanding the meaning of information about a destination, the receiver will send a query. Hey, I got your summary, I'm happy, but I want more clarification on this A.A.A.8 destination. I want more clarification. I want more information on this particular network. That's what LSR, link state request. I repeat, this is not sent after 10 hours. This is sent right in the beginning when they are forming adjacency. We are going to learn later, in a few minutes later, 7 stages of forming adjacency. In there, you will see a place called loading. That is the place where LSR and LSU is exchanged. LSR is link state request, where the requests for detailed information about a destination is asked. As a response, the detailed information about the destination is given in the form of LSU. At last, you have LSAC, link state acknowledgement. LSAC is sent whenever someone receives DBD. LSAC will be sent whenever someone receives a request, then also acknowledgement will be sent. Whenever someone receives update, then also acknowledgement will be sent. Acknowledgements are sent for all these 3. Now, how often hello packets are sent? As you said, during the revision time, you say 10 seconds. You're right. Every 10 seconds, the hello packets are sent. And if someone is not saying hello for 40 seconds, 4 times, that someone is considered to be dead. Now, this is a slice of a packet. After layer 3, if you see here, see this is data link layer. This is layer 3. In layer 3 itself, you'll see a protocol number, which means OSPF is next. In the OSPF header, these are the fields you will find. First, the version number. I showed you here. Wait, let me take you. You see, the version number. received OSPF packet. R1 is receiving a OSPF packet. Via this interface, the OSPF packet is coming. And what you see in the first field is a version. Yes, please. Yeah, don't worry. Yeah, yeah. Okay, very nice. You see, router ID is to identify the router uniquely within an area. And now you know what is AID. Okay, I repeat the statement. Listen. Router ID is the name for a router to be identified within an area. Ah, so the router has got two ID. Correct. This is area 1. Area ID is 32-bit. But mostly you don't see people typing the 32-bit. You don't see people typing 0.0.0.1. If you say 1, it will take it as 0.0.0.1. Yep. So if you go back here also it is explained. Version, type. What type you saw there? It's a hello packet, type 1. And then the length of the packet, packet's length. Packet's length is 48 bit. And then the router ID. Yeah, router ID. Router ID is again 32 bit. We'll talk about more about router ID a bit later. Area ID. To which area the router belongs to. The checksum value is for integrity, to make sure that the packet is not altered in the path. And then the authentication type. There are 3 types of authentications in OSPF, which we'll see later. And this is type 0 here, means null authentication, no authentication. And then the authentication string means the authentication itself, the password itself. This is type 0 and there is authentication itself. And then the payload data. Oh, come on. You don't see those things in debug, but if you will capture a packet through Wireshark, you may see. So these are the fields that we will find. Now, forming neighborship, maintaining neighborship is, recovering neighborship is done through sending hello packets. Forming neighbor, it sends a hello packet every how many seconds? Exactly. Every 10 seconds they send hello packet. And there are a few parameters that should match in order to form neighbor. Inside the hello packet, the parameter sent router ID, we just saw router ID is also carried in the packet. Not only that, even the timers are shared in the hello packet. The timer must match with the neighbor. If you wish to change the timer, you are free to do that, but make sure you do it on every router. Why? You see here, it has got the asterisk. All that asterisk must match with the neighbor. If the timer don't match with the neighbor, don't expect neighborship. Next, the neighbor list. The neighbors list. So when B router send hello packet, it will have a list of neighbor which it already know. For example, if B knows already D, in the hello packet of B, the information about D will be going. And when A receives it, he understands that I know B now and B already knows D. So the neighbor informations are also shared in the hello packet. Don't forget the neighbor informations are always shared. The neighbor table is always shared in the hello packet. Area ID. That is to tell to which area this router belongs to. That is the area. To which area the router belongs to. And you yourself told me that area ID must match in order to form neighbor. Yeah. This is how it knows that what area the neighbor belongs to. When a neighbor router sends a hello packet, I compare my own area to the hello packets of my neighbor. When it matches, I accept. Otherwise, I deny. So so far we have seen 4. In that 2 should match. What are they? The area ID and the time interval. The router priority. The default priority in a LAN environment is 1. The default priority in a LAN environment is 1. Do you know the priority in the WAN environment? Exactly. In a WAN environment, meaning we call it a serial wire, the priority is always 0. What if I change the priority? If you want to change the priority, definitely you can do that. But it's of no use. The priority is of no use in a WAN environment because the priority is used in electing DR-BDR. Do we have DR-BDR in a WAN environment? In a point-to-point, do we have DR-BDR? You're in silent. The priorities are always 0, and if you try to change the priority, it's of no use because there is no DR-BDR election in a WAN environment. LAN environment, of course, we need priority in order to alter the DR-BDR default selection. We'll talk about that when we go there. Now, what I'm trying to say here is the priority is also shared in the hello packet. Only then, in a LAN environment, one router will know about the other router's priority to decide who can be a DR and BDR. And then you will also see the DR BDR IP address. and then the password if you have enabled, and then the stub flag. So there are special network types that OSPF supports. Stub networks, totally stub, not so stub, totally not so stub. Likewise, we have some stub types. Even those informations are shared in the hello packets. The stub area flag must match in order to form neighbor. So here are few but most important things of hello packets parameter, among which the timer, the area ID, the authentication string, and the stub should match. Now, do you have any question on this page? Sorry, you are in mute. Okay. Okay, do you have any question on this page? Now, I want to ask you a question. Will you be okay? All right. Is there any need for the router ID to be matched? Yeah. What if two routers have got same router ID? Very correct. Now they will they form neighbor or not? Correct. All right. Now there are 7 stages in forming adjacency. OSPF adjacency stages. And this adjacency is bidirectional. For example, you have already configured router A and just finishing the router B configuration. A is configured already, B you're finishing it. A is already configured. So B is still not fully finished, you are finishing, almost finishing. So there is no OSPF because it is not fully configured. It will be in a down state. The relationship between A and B is going to be in down state. But A will be keep on sending its hello packet to a multicast address. What is the multicast address of OSPF? 224.0.0.5. So to this address, it keeps sending hello packets saying, "Hey, I'm router ID so and so, and I don't have any neighbor. I don't see anyone. I don't have any neighbor. I'm here. If anyone wants to add me as a neighbor, please add me." So that hello packet, we call it as init packet, initialization, initiating packet. What it is initiating? It's initiating the OSPF adjacency. OSPF adjacency. Now, the init state will be promoted to two-way state if B is already ready and B is ready to send the hello packet. Now you see B is ready. From the init, B learned. From the init packet, B has learned that I got a neighbor called 172.16.5.1. So router B, when it sends its hello, In the hello, we saw that there will be a neighbor list, you see. In the hello, they also explain who their neighbors are. So the neighbor list is sent. B is sending the hello packet in which the neighbor list is sent. In the neighbor list, the information of router A is already there. So router B says, hey, it's me, 5.2, and I already have a neighbor, 5.1. And it comes to A as a unicast. Now A finds its own address. A finds its own address as the neighbor's neighbor. A now knows that B already know me. And A adds this IP address in its neighbor list, which means both know each other. That is what called as two-way state. See, both knowing each other in not in detail. They know only the router ID. That doesn't mean that you know about me everything. You know my name, that's all. Jay. I know your name, Robert. That doesn't mean that I know you completely. Yeah, we know each other, but I don't know your address. I don't know your education background. I don't know where you work. I don't know your friends. I don't know your family. I know nothing. But I know one thing, your name. So knowing your name is not really knowing someone. It is just a two-way state. I know you, you know me. How much you know? Just the name. How much I know? Just the name. Right, so two-way state is just knowing the neighbor's router ID. That's all. It's important to know what is two-way state. Two-way state, you see, they don't share any LSDB or LSR, LSU, nothing. They know each other by name, that's all. Now, after two-way state, only with the DR and BDR, only with the DR and BDR, the other routers will go to the start state. The previous chapter we learned that full adjacency is formed only with the DRs. That is what now getting started. Forming full adjacency. To form full adjacency, if you stay in two-way state, it's not possible. Between the other routers, they stay in two-way state. But with the DR, all the router will now try to form adjacency. For that, they have to first come to a conclusion who is big and who is small. Yeah. In this start state, exchange start. Before we start the exchange, before this two router starts exchange, let me give a name to this, A and B. Before A and B start sending some DBDs, database description, They have to come to a conclusion who will initiate the exchange, who will first begin the exchange. See, both should not send at the same time. If we both talk at the same time, we cannot understand fully. But when I speak, you are listening. When you speak, I am listening. So that's important even in networking. So both the routers cannot exchange at the same time. They want to exchange DBD. Both wants to give their DBD, but who will do first is determined in this extract state. For example, here you see this guy A is saying, I'll start the exchange. I have this as the route ID. Router A says, hey, this is my route ID. I'm going to exchange. Now router B compares its own route ID with this route ID and says, hey, no. I will start the exchange. Why? Because my router ID is higher. My router ID is higher. I'll start the exchange. You be silent. After I send, you can send. This is what we call it as extract state. Extract state is the place where they decide who will initiate the exchange, who will start the exchange. And once they come to conclusion, they start exchanging. That's called exchange state. So extract state after followed extract, that is exchange state. This is where I was talking about DBD. DBD is a summary of LSDB. So the first person to share the DBD is the one with the bigger router ID. It says, hey, this is my DBD. Take it. And followed by A is sending its DBD. This is my DBD. So they both have exchanged the DBD. Of course, the acknowledgement is also sent. It is not shown here. Once A receives the DBD, A will say, thank you, I received your DBD. Here is my DBD. And B says, okay, thank you. I received your DBD. So B with the router ID 172.16.5.3 will share the DBD first, followed by A, because the one with the bigger router ID should send. If priority would have been set, let's say here the priority is the default. Here if I would have said 100, this would have become DR, not this. And this would have shared the DBD first. DBD should be shared by the DR. And DR is elected first by comparing the priority. If the priority is same, only then they compare the router ID. If the priority is same, only then they compare the router ID. In the picture here, in the example here, they are not talking about priority, they only talk about router ID. But before router ID, what it will check? Priority. The priority default is 1 in a LAN environment. In a WAN environment, on the serial link, they don't have priority, there's 0 priority. They compare only the router ID. The one with the bigger router ID will exchange, followed by the other one which is smaller. So this is how the exchange of DBD happens. But I told you the DBD is a summary of LSDB. So there may be need for a clarification. That is where the loading state comes. Okay, here is the acknowledgement for DBD. And here is the loading state comes, where they clarify their doubts. Router A is sending, hey, I need complete information about this network. And B is saying, oh, here it is, the complete information. That is what called as LSR and LSU. When they don't have any more LSR to ask, they reach the final full state. Full state is fully synchronized. They know each other very well. That's full state. Now, let's quickly do a revision. OSPF adjacency. From the down state, they move on to initialization state by sending the hello packet. The other router will know the router ID of the sender. The router ID of the sender is written into the neighbor table. That is init state. And then the other router now send a hello packet in which there will be a neighbor list. When the receiving router finds its own router ID in the neighbor list, they both move on to a state called two-way state. Two-way. Meaning they know their router ID via the neighbor list. They know each other. Next is they both need to now decide who will initiate the exchange. Who will initiate the exchange? They compare their router ID. From the hello packet, they know other routers' router ID. They compare the router ID. The one with the bigger router ID will say, I'll initiate the exchange. This decision is made in the start state. Once the decision is made, they start exchanging as per the decision. The one with the bigger router ID always initiates the exchange. The other one will follow. We call it as exchange state. What they are exchanging is summary of LSDB. Summary of LSDB is what they are exchanging. Because it's a summary, there may be a query which is sent as links to request. For the query, the response is given as links to update. When there is no more query, they reach full state. So for this LSR, LSU, acknowledgement is sent. DBD, acknowledgement is sent. Do you have any question in OSPF adjacency? Very clear with the concept? Again, you are in mute. Sorry to you. In a LAN environment, we got too many routers. This is one of the important topic in OSPF. We should have a very clear understanding on why DR, BDR, all the stuff. Do you know why we need DR, BDR? Yeah. So what you said is correct. We got many routers. When you have many routers, and when it is connected through a LAN switch, connected through a LAN cable. Now, I'll call this as A, B, color is too dull. A, B, C, D. If all these routers talk each other, problem. Why? For example, let's say D is sending an update. It goes to everyone. If this everyone send it to others, what will happen? Duplicate. D sent to everyone. Using a multicast address, let's say 224.0.0.5. Now, E, after receiving it, if it send again to 224.0.0.5, then it will become a duplicate. And B, after receiving it, if it again send to everyone, then it will become a duplicate. And when a packet comes, B will think E has got it, E will think C has got it, C will think E has got it, A will think D has got it. So there's going to be a loop. So what is needed is a leader. Let us say this is the leader, designated router. And we got a backup designated router. Let's say this is backup designated router. How this is elected? Based on the priority. Let's say I give priority 10, priority 20. Sorry, priority 5. And these are all default priority. So the DR is elected now here based on the priority. What if the priority is same? How the DR will be elected? Please unmute and Mhm. Mhm. Router ID. Router ID. They will compare the router ID. We saw that in the hello packets, the router IDs are exchanged, isn't it? The router ID is the IP address, the biggest IP address on the router. So the router ID is the biggest IP address on the router. Each router will definitely have only one, at least, not at least. Yeah, at least they will have only one IP at least, either in the loopback or physical, whatever. So that address, the one highest IP address is picked up. We'll talk about that later, the DRBDR election. Now, what I'm trying to say here is, why do we need DRBDR? We want to avoid loop. Why loop is occurring if you don't have DRBDR? Because everyone will have the privilege of talking to every other router. Then there are chances of repeating the same routes that are already replicated. So we we see that OSPF elects BDR using the priority. Okay, now the BDR is elected. The update should be sent only to DR. If an update is coming, the update is sent only to DR. Only to DR. When I say DR, it includes BDR. But BDR will not share with anyone because BDR is a backup. It is not a primary. Now, the DR will replicate this information to others. Now, there is no loop because C and B has got no privilege of talking each other. If C and B wants to talk, they can talk only to E and A. C, B, D, they don't have privilege to talk to each other because they stop in two-way relationship. They are called as DR other router. DR other router, they don't have privilege of talking each other. They have only two-way relationship. But D has got full relationship with DR and BDR. C has got full relationship with DR and BDR. But between the other routers, they will have full two-way relationship. With two-way relationship, do they exchange? In two-way relationship, two-way comes after or before exchange. Sorry, exchange comes after two-way or before two-way. Exactly. Exchange comes after two-way. That's what we saw. Exchange comes after two-way. Here, they all stop in two-way relationship. They're not going to exchange. Now, how is this achieved? How is this achieved? How can, when an update comes, it talks only to A and E? For the DRs to listen, there's a special address called 6, 224.0.0.6. Please listen carefully. Whenever there is a DR BDR elected, there is a new multicast address in use. We saw earlier 224.0.0.5 is the multicast address of OSPF. Yes, that is true. For point-to-point and this multi-point, this address is used, but there's a special address added. This address, if you send any traffic, only DRs can receive. Only these two guys can receive the packet. If you are sending the packet to this address, only these guys can receive because they only own that address. And now they use, after receiving the update, E uses 224.0.0.5 to give the update to others. When you send any traffic to this address, all can receive. This is how we are able to separate who talks to whom. You see, there is a link state change. There is a link down. Notification is sent to 6. Why? Because it wants to send only to DRs. And the notification is now distributed by the DRs using 5. Is it clear? So who uses what address is very important. Shall I ask you a question? It will be a little tricky. Are you okay? What is the address the other router listen to? Exactly. What is the address that DR will use to distribute the update to others? Exactly. Right. What is the address that DR family listen to? Exactly. Very well understood. Now, mhm, only a few more pages. Let's finish this chapter, please. Now, you see, the sequence numbers are very important. In the previous class, I was telling you, whenever there is a new change, the sequence number will get incremented. But what is the sequence number? Is it alphanumeric or decimal or hexadecimal? What sort of number it is? It is actually 4-byte number. Starting from this, ending in this. Beginning with this, ending with a C. If you begin with 1, you can end with F, right? That is hexadecimal. Now, once it has reached all these bits F, it gets resetted to 8 here. So that again it can start from this number, go up to F, and then it goes to 7 so that the next number will be 8. Again it can start again. If it reaches 9, it cannot start from here again. You understand? So when it reaches F, 8 becomes 7 so that it can go and restart from here, from 8. You got it? Listen. It starts from where? 8, right? And these are all 0. And when this all becomes F, what this is supposed to become? 9, 0, 0, 0. But if it goes 9, then it cannot fit into 4 bytes. So you need to come back to this number 8. How you can come back to this number 8? After 9 comes 8 or after 7 comes 8? That's why. When all these bits are turned F, by incrementing 1, 1, 1, 1, every changes that happens, it increments by 1. When all this 0 becomes 1, instead of switching to 9, it switches to what? 7. So that it can start from 8. You understood now? Very, very nice. So this is how the sequence number gets incremented, and when it reaches full, it gets resetted back. But again, I'm telling you, this will never become full like this. It's very rare. Why, Every 1 hour, they reset. See, they wrap around to this number. Even if it's a very big network, within 1 hour, you cannot reach from here to here. Even in a big network, lot of changes, still you cannot reset that fast. So it is getting wrapped around like this after 1 hour, every 1 hour. And I already told you every 30 minutes they want to send the update periodically to make sure that there is no change. make sure they're all fully synchronized. When a router encounters two instances of LSA, it is going to determine which is reset based on the newer sequence number, the higher sequence number. That's how sequence numbers are used. This we learned in the first chapter end. You remember there was a flow chart. Yes or no? Newer the number, that's the latest. Now, how do we verify this? If you type show IP OSPF database, you can see the sequence number. This is the eighth update from this advertised router about this link. And this is the sixth update from this neighbor about this link. Yeah. So this is 48 seconds before you got, this is 212 seconds before you got. This page I already explained to you, the debug. In the lab session, I will show you by capturing using Wireshark when I do the lab. Right, so this chapter was about the packet types. OSPF, packet types. And also we saw the adjacency states, 7 stages. And also we saw why DR, BDR elected. And also we saw what address is used by DR to send the update and what address is used by others to send the update. Can you say for one last time what address is used by DR to send the update? No. Yeah, okay, by the DR file. You're right. All right, now how often the sequence number gets resetted? Well said, exactly. Any questions for me? So in this chapter, okay.